Hello students, welcome to the lecture on thermochemistry, and after this lecture we will be able to learn the following objectives. Explain the flow of energy, heat and work. Describe the enthalpy changes. Define the heat in changes of states. Understand the calculating heats of reaction. Understand entropy and free energy. Let's start with what thermodynamics is. Thermodynamics is a unique theory because it looks only at the macroscopic properties of matter and on that basis alone tries to predict what other macroscopic behavior exists. Example, whether a particular reaction will occur or not under certain conditions. It is based on a few basic tenets and is a very general theory. In fact, if the entire atomic theory of matter were overthrown, that is electrons, neutrons, protons, atoms, molecules, the foundations of thermodynamics would still be sound. The first law of thermodynamics. Energy can be converted from one form to another, but can be neither created nor destroyed. This is also known as the law of conservation of energy, or more simply stated, you cannot get something for nothing. In this context, we will talk about the two forms of energy. Potential energy, due to position or composition of object. Kinetic energy, due to motion of object. Heat, in general, any energy process that transfers energy into random atomic and molecular level motions is called heat. Heat is not a form of energy. It is only a process in which energy is transferred. Remember, energy only exists as potential or kinetic energy. Temperature is related to heat in the sense that temperature is a measure of the random motion of the atoms and molecules in a particular substance. When two objects at different temperatures are placed together in contact, energy will be transferred between the two objects by the process called heat. Work. I can also transfer energy into my system of the marble and bowl by lifting the marble up and restarting the oscillation. This type of energy transfer into our system is called work. Work can be calculated given the forces that applied onto an object over a given distance. Just like heat, work is not a form of energy, but rather it is only a process in which energy is transferred. Summing it all up, there are only two forms of energy, kinetic and potential. There are only two ways to transfer energy, heat and work. State function. Property of a system that does not depend on the previous history of the system, only its present condition. Certain parameters describing the system will be independent of the history of the system. For example, the difference in energy between a liter of water at 0 degrees Celsius and a liter of water at 100 degrees Celsius is the same no matter how many times the liter of water was heated and cooled down. In contrast, heat and work are not state functions. Without knowing a system's history, we cannot know how much energy was lost or gained by a system in the form of heat or work. In general, we conclude that delta E is greater than 0, positive, EF is greater than EI, means system gained energy from its surroundings. Delta E is less than 0, negative. EI is greater than EF, means system lost energy from its surroundings. More specifically, we have, if Q is greater than 0, then energy was added to the system as heat. If Q is less than 0, then energy was lost from the system as heat. If W is greater than 0, then energy was added to the system as work. If W is less than 0, then energy was lost from the system as work. In chemistry, we define the reactants and products as a thermodynamic system. Exothermic reaction. Reaction that gives off energy as heat to its surroundings, that is, Q is less than 0. Endothermic reaction. Reaction that absorbs energy as heat from its surroundings, that is, Q is greater than 0. Thermodynamics deals with energy in its various forms and the conversion of one form of energy into another. Energy appears in several different forms: kinetic energy, potential energy, heat, chemical energy, and so on. Kinetic energy is energy of motion. It is written as Ke equal to half mv square, where m is the mass of a moving object and v is its velocity. Potential energy has many different forms depending on the physical system at hand. For example, local gravity, Hooke's law, compression of a spring, Coulomb's law, large-scale gravity. Kinetic and potential energy are interchangeable and both can be converted into work. Mechanical work is a force times the distance through which it acts, that is, dW is equal to Fdx for one-dimensional motion. Work for a finite motion is obtained by integrating equation 2, where the f of x takes into account the possibility that the force may be changing as one moves along the path from x1 to x2. Work can increase the kinetic or potential energy of a system. Energy transformations. Energy is the capacity to do work or to produce heat. There are many forms of energy, each of which can be classified into three categories: radiant energy, kinetic energy, and potential energy. Energy can be changed or transformed from one form into another. Energy transformation is also called energy conversion. Kinetic energy is the energy of an object in motion. An object in motion can cause another object to do work by colliding with it, causing it to move in a particular distance. The colliding objects can be a hammer swinging down on a nail or two atoms colliding in a chemical reaction. Examples of kinetic energy are mechanical energy caused by motion of parts and thermal energy caused by the random motion of particles of matter. An object that has potential energy is not moving or doing work. At some point, that objects had work performed on it which resulted in energy storage. One example of performing work on an object to give it potential energy is the action of winding a watch. Conversion between potential and kinetic energies is quite common. As the potential energy of an object increases, its kinetic energy tends to decrease. Likewise, if the kinetic energy of an object increases, its potential energy decreases. Most chemical reactions involve transformations in energy. A chemical reaction is simply the process whereby bonds are broken between atoms and new ones are made. When bonds are broken in a chemical reaction, the reactants involved are colliding with sufficient kinetic energy to break the atomic bonds apart. Exothermic and endothermic process. Exothermic. The word describes a process that releases energy in the form of heat. Forming a chemical bond releases energy and therefore is an exothermic process. Exothermic reactions usually feel hot because it gives heat. Endothermic, a process or reaction that absorbs energy in the form of heat. Breaking a chemical bond requires energy and therefore is endothermic. Endothermic reactions usually feel cold because it takes heat. Heat capacity and specific heat. Heat capacity of an object is the amount of energy needed to increase the temperature of a substance by 1 degree. Heat capacity is equal to heat supplied upon temperature rise. The heat capacity of an object depends on both the quantity and types of matter in the object. Specific heat is the quantity of heat required to raise the temperature of 1 gram of material 1 degree Celsius or 1 Kelvin. We get the specific heat when we divide the heat capacity of a material by its mass. Specific heat is equal to heat capacity by mass is equal to C by M. To find the heat Q required to raise the temperature of a sample by a certain amount, you multiply the specific heat of the substance S by the mass in grams M and the change in temperature delta T. Specific heat capacity. The specific heat capacity of a solid or liquid is defined as the heat required raising unit mass of substance by 1 degree of temperature. This can be stated by the following equation where delta Q is equal to heat supplied to substance, M is equal to mass of the substance, C is equal to specific heat capacity, delta T is equal to temperature rise. 4 quantities called thermodynamic potentials are useful in the chemical thermodynamics of reactions and non-cyclic processes. They are internal energy, the enthalpy, the Helmholtz free energy and the Gibbs free energy. Enthalpy is defined by H is equal to U plus PV, where P and V are the pressure and volume and U is internal energy. Enthalpy is then a precisely measurable state variable since it is defined in terms of 3 other precisely definable state variables. It is somewhat parallel to the first law of thermodynamics for a constant pressure system. Q is equal to delta U plus P delta V, since in this case Q is equal to delta H.
So enthalpy is a thermodynamic quantity equivalent to the total heat content of a system, equal to the internal energy of the system plus the product.
I did not get any of that.
Okay, in simpler words, enthalpy is a measure of the total energy of a thermodynamic system. It includes the internal energy, which is the energy required to create a system. But before I tell you the rules to determine the enthalpy change, do you know what exothermic reactions and endothermic reactions are?
Yes, exothermic reactions are the reactions in which heat is released, and endothermic are the ones in which heat is absorbed.
Very good. Remember some of these facts. The activation energy is required to start reaction. Delta H is the change in heat energy between the products and the reactants.
And the unit for delta H is joules, kilojoules or calories.
Good job. Now let me ask you a question. Will the value of delta H be positive or negative for exothermic reactions?
Negative, because the energy needed for the reaction to occur is less than the total energy released.
Excellent. Now what about the value of delta H for endothermic reactions?
Positive, because the energy needed for the reaction to occur is more than the total energy released. Does that mean if you double the coefficients in an equation, then the value of delta H is multiplied by 2?
That's right. Here's an example.
So we multiply H2 and O2 by 2, and the product side gets multiplied by 2 as well.
That is a true statement, but do not forget to multiply the delta H. Remember, this law is commonly applied to phase changes, although it is true when you reverse any thermochemical reaction.
Give me an example for this one too.
Here you go.
So basically, the signs for delta H gets reversed.
Another way to look at it is to remember that delta H is a state property, so it must be independent of the path of reaction.
So if reaction 1 plus reaction 2 is equal to reaction 3, then delta 3 is equal to delta H of 1 plus delta H of 2.
Heat reaction is equal to the heat formation of products minus the heat formation of reactants. Let's do an example. The combustion of methane gas. Heat of formation of CO2 plus 2 times heat of formation of H2O minus heat of formation of CH4 plus 2 times heat of formation of O2.
So, the heat of combustion, that is, the heat of reaction, is minus 802.3 kJ per mole of methane.
Notice that the value is negative, so the reaction gives off heat as expected for a combustion reaction. Entropy is a thermodynamic property that can be used to determine the energy not available for work in a thermodynamic process, such as in energy conversion devices, engines. The following are in order from least to most amount of entropy.
Solid, liquid, gas.
Let's think about it. Solids have minimum entropy and maximum order, whereas liquids have maximum entropy and minimum order. The greater the disorder or randomness in the system, the larger the entropy.
First law of thermodynamics. This law deals with the fundamental concept of energy, work and heat and the relation between them. The first law of thermodynamics simply says energy is conserved. Therefore, it is also known as the law of conservation of energy. Energy can neither be created nor destroyed. However, it can be transformed from one form to another. Since energy is related to mass by the relation E is equal to mc square, this law can also be stated as the total mass and energy of an isolated system remains unchanged. Suppose a system which possesses an internal energy E1 in its initial state is given a heat Q. The heat taken up by the system can be used to increase either its internal energy or perform work, or may be used for both the purposes. If the energy of the system increases and attains a value E2 in the final state, then E2 minus E1 is equal to E delta is the increase in the internal energy. Further, if W is the amount of work done by the system, then the law of conservation of energy requires heat absorbed by the system is equal to increase in internal energy of the system plus work done by the system. That is, Q is equal to E delta plus minus W is equal to delta E minus W, or delta E is equal to Q plus W. The minus sign of work appears as work is done by the system on the surroundings, so the internal energy of the system decreases. Equation 3 also suggests that when Q amount of heat is given to the system and at the same time W amount of work is done on the system, then the internal energy of the system is increased by delta E. For infinitesimal small changes, equation 5 can be written as dE is equal to dQ plus dW, where dQ is the amount of heat given to the system, dE is infinitesimal changes in the internal energy, and dW is the work done by the system. If only expansion work, pressure minus volume work, the work arising from a change in volume is considered, then one can write dW is equal to minus P dV. So equation 5 can be written as dE is equal to dQ minus P dV. If the volume of the system is kept constant, that is, no work is done, then dV is equal to 0, and equation 6 reduces to dE is equal to dQV, or delta E is equal to QV. Further, for a cyclic process, delta E is equal to 0. Therefore, equation 5 becomes Q plus W is equal to 0, or Q is equal to minus W is equal to work done by the system. According to this equation, the total heat given to the system is utilized in doing work by the system. Heat change at constant volume Q, V. From the definition of first law of thermodynamics, we can write Q is equal to delta E minus W, and in terms of work of expansion, Q is equal to delta E plus P delta V. At constant volume, delta V is equal to 0, so we can write Q V is equal to delta E. Thus, at constant volume, the heat absorbed is equal to the increase in energy of the system during the process. Heat change at constant pressure Q, P, enthalpy H. Several chemical and physical processes generally occur at constant pressure rather than at constant volume, since most of the reactions are carried out in an open system instead of in a closed system. Thus, at constant pressure, the total heat given to the system is used in increasing its internal energy and doing the work of expansion. The first law enables us to write Q P is equal to delta E plus P delta V, or Q P is equal to E2 minus E1 plus P, V2 minus V1, or Q P is equal to E2 plus P V2 minus E1 plus P V1. At this stage, a new thermodynamic function H, called the enthalpy or heat content of the system, must be introduced, which expresses the thermal changes at constant pressure and is defined as H is equal to E plus PV, where E is the internal energy and P and V are pressure and volume of the system. Changes in the state of a system are produced by interactions with the environment through heat and work, which are two different modes of energy transfer. During these interactions, equilibrium, a static or quasi-static process, is necessary for the equations that relate system properties to one another to be valid. Heat. Heat is energy transfer due to temperature differences only. Heat transfer can alter system states. Bodies do not contain heat. Heat is identified as it comes across system boundaries. The amount of heat needed to go from one state to another is path dependent. Adiabatic processes are ones in which no heat is transferred. Zeroth law. There exists for every thermodynamic system in equilibrium a property called temperature. Equality of temperature is a necessary and sufficient condition for thermal equilibrium. The zeroth law thus defines a property, temperature, and describes its behavior. Note that this law is true regardless of how we measure the property, temperature. Work. Heat is a way of changing the energy of a system by virtue of a temperature difference only. Any other means for changing the energy of a system is called work. We can have push-pull work. Example, in a piston cylinder, lifting a weight. Electric and magnetic work. Example, an electric motor. Chemical work, surface tension work, elastic work, etc. In defining work, we focus on the effects that the system, example an engine, has on its surroundings. Thus, we define work as being positive. When the system does work on the surroundings, energy leaves the system. If work is done on the system, energy added to the system, the work is negative. A system's condition at any given time is called its thermodynamic state. For a gas in a cylinder with a movable piston, the state of the system is identified by the temperature, pressure, and volume of the gas. Thermodynamic equilibrium. A particularly important concept is thermodynamic equilibrium, in which there is no tendency for the state of a system to change spontaneously. Temperature. The concept of temperature is fundamental to any discussion of thermodynamics, but its precise definition is not a simple matter. With the definition of equality of temperature in hand, it is possible to establish a temperature scale by assigning numerical values to certain easily reproducible fixed points. Calculating heats of reaction. Thermo chemistry deals with the study of heats of chemical reactions. When a chemical reaction takes place, energy in various forms may either be emitted or absorbed. The study of the heat produced or required by chemical reaction forms the basis of thermochemistry. Reactions in which heat is produced are called exothermic reactions, whereas those in which heat is absorbed are known as endothermic reactions. In an exothermic process, at constant pressure, the enthalpy change is negative. That is, delta H is less than 0. On the other hand, absorption of heat leads to an increase in enthalpy. Thus, endothermic process at constant pressure has positive value of enthalpy change, that is, delta H is greater than 0. Heat of reaction. The heat of reaction is defined as the amount of heat liberated or absorbed at a given temperature when the reactants are converted into products as represented by the balanced chemical equation. If Q is the heat of reaction, W the work done by the reactants during reaction, then according to the first law of thermodynamics, one can write Q is equal to delta E minus W. Thus, the heat of reaction at constant volume, QV, is the change in internal energy of the system during a chemical reaction. However, if the chemical reaction is carried out at constant pressure in an open calorimeter, then W is equal to minus P delta V, and in that case, QV is equal to delta E minus P delta V is equal to delta E plus P delta V is equal to delta H. Hess's law, the law of constant heat summation. G.H. Hess in 1840 experimentally gave the second law of the thermochemistry, which has important applications and is known as the law of constant heat summation. This law may be stated as the net heat change in a chemical reaction, either at constant pressure or at constant volume, has the same value whether it occurs in one step or in several steps. Thus, according to this law, the resultant heat change in the reaction depends only on the initial and final states and not on the intermediate steps through which the final state is achieved. Another important significance of this law is that the thermochemical equations, like algebraic equations, can be added or subtracted. Applications of Hess's law. Hess's law has several important practical applications for determining heats of formation, heats of reaction, and heats of transition of substances, which cannot be measured directly by experiments. Determination of heat of formation of substances. The law of constant heat summation is conveniently used as an alternative procedure to calculate the heat of formation, delta HF of those substances for which heat of formation cannot be determined by direct experiments. This introduces the thermodynamics of chemical reactions. To start, imagine the following demonstration. Cold packs contain separate compartments of water and a salt such as ammonium nitrate. When we mix the salt and water, the cold pack gets cold. Such a reaction is called an endothermic reaction. This reaction is spontaneous, even though thermal energy is needed to break the ionic bonds of the crystalline NH4NO3. Spontaneity and Gibbs free energy. The entropy must be included to predict if a reaction will be spontaneous. The total change in the available energy of a system is called the change in the Gibbs free energy, where delta G is the change in Gibbs free energy, kilojoule per mole. Delta H is the change in enthalpy, kilojoule per mole. T is absolute temperature in K. Delta S is the change in entropy, kilojoule per mole K. The change in enthalpy is the amount of heat or work that is transferred when a reaction occurs. A reaction is spontaneous if delta G is negative, that is, the products have a lower Gibbs free energy than the reactants. The second law of thermodynamics, the entropy law or law of entropy, was formulated in the middle of the last century by Clausius and Thomson, following Carnot's earlier observation that like the fall or flow of a stream,
entropy is a thermodynamic property that can be used to determine the energy not available for work in a thermodynamic process, such as in energy conversion devices, engines. The following are in order from least to most amount of entropy:
solid, liquid, gas.
Let's think about it. Solids have minimum entropy and maximum order, whereas liquids have maximum entropy and minimum order. The greater the disorder or randomness in a system, the larger the entropy. The entropy of a substance always increases as it changes state from solid to liquid to gas. When a pure solid or liquid dissolves in a solvent, the entropy of the substance increases. When a gas molecule escapes from a solvent, there is an increase in entropy. Entropy generally increases with increasing molecular complexity. Reactions that increase the number of moles of particles often increase the entropy of the system. Here's a question for you, buddy. Which of the following reactions results in the largest increase in entropy? A. CO2-CO2. B. H2 plus Cl2 to HCl. C. KNO3-KNO3.
All of the reactions result in an increase in disorder, but A, in which CO2 moves from a solid state to a gaseous one, represents the largest change in disorder. We can calculate entropy using a table of standard values in much the same way that we calculated enthalpy earlier.
Application of the laws of thermodynamics to chemical systems allows chemists to predict the behavior of chemical reactions. When energy and entropy considerations favor the formation of product molecules, reagent molecules will act to form products until equilibrium is established between products and reagents. The ratio of products to reagents is specified by a quantity known as an equilibrium constant, which is a function of the energy and entropy differences between the two. What thermodynamics cannot predict, however, is the rate at which chemical reactions occur. For fast reactions, an equilibrium mixture of products and reagents can be established in 1 millisecond or less. For slow reactions, the time required could be hundreds of years. Entropy changes in an ideal gas. Many aerospace applications involve flow of gases, example air, and we thus examine the entropy relations for ideal gas behavior. Now in the end, let us summarize what we have learnt in this lecture. Thermodynamics deals with energy in its various forms and the conversion of one form of energy into another. The heat capacity of an object is the amount of energy needed to increase the temperature of a substance 1 degree. The specific heat capacity of a solid or liquid is defined as the heat required raising unit mass of substance by 1 degree of temperature. The zeroth law thus defines a property, temperature, and describes its behavior.